So today we're going to be doing the Brainpan CTF, which is a buffer overflow. So we're going to be doing this box while explaining the theory and coding the scripts. So let's get started. You can see I've run another net discover and describe the IP .131. Again, I'm using a host only network. And for the sake of time, I'm not going to run a port scan or anything, but the port 999949 is the one with the vulnerable server, and port 10,000 is the one with is a web server. So for the sake of time, you can dir bust for this bin directory, and the executable for the server is here. And if you were to go here and connect to the server, you'd see the prompt, and this is what this executable actually is. It's this thing right here. So what we're going to do is fuzz this this server. So I've attached the executable to the Mona debugger, or sorry, not the Mona, Immunity debugger, which you can download from here. And all you have to do is go File, Attach, and then choose that one. So you can see a bunch of stuff. You don't really have to pay attention, but over here you can see the registers, and these are really important. So our goal is to overflow the EIP, or extended instruction pointer. And the way this works is that there will be a buffer, or a allocated set of bytes that the server has for us to send to it, and it doesn't properly check the length. So that means if the buffer allocated, say, 700 bytes, we could send more than 700. And what happens when we send more than 700 bytes is we write to memory that we shouldn't be able to write to, nearby memory. And in this case, after we overwrite the stored base pointer and local variables, we can overwrite the return address. And all the return address is when you have a call instruction, like this one right here, or this one, it will push the address of the next instruction, so this thing right here, onto the stack. And then when you get to a ret instruction, when you're leaving the subroutine, it will essentially pop this address into the instruction pointer and jump to it. Meaning if we can overwrite the return address, we can change where the executable jumps to next. So we can change the way the executable functions. And the way this works is we fill the buffer in reverse order, so we write towards the instruction pointer, not away from it, which is a little kind of counterintuitive. Live Overflow and Computer File have excellent videos on this if you want some more technical explanations. So here is our first script, and this is my IP address, so I'm hosting the executable on my Windows machine here, port 999, and all we're doing is we're importing socket, we're making a socket, and we're making a buffer of 1000 A's to try and fuzz this to cause a crash, see if we can overwrite the instruction pointer. We connect, and then with Python 3 you have to encode your bytes, and then we're going to receive it. So let's get started here. Let me open up a new terminal, go to the desktop, obligatory color A, and we're going to run the file Brainpan1. Hang on a second. This isn't started correctly. Let me just run it. And now you see it's actually listening. My bad. So one more time. And you see we have overwritten the instruction pointer with 41414141, which, if you translate that into ASCII, is AAAA. So we've successfully overflown the EIP. Now we need to figure out the exact number of bytes it takes to reach the instruction pointer. So in order to find out how many bytes that is, we're going to use a pattern. So going to our next script, we see the same thing: import socket, make a socket, and then we have this pattern, which is a unique string. And what it'll do is, I use this online generator because I don't have host to guest or guest to host copying in my virtual machines. But I said 1,000 characters. I think it might have done 10,000. But all it does is it'll send this unique string to the server, as you can see right here, and then you will look at the EIP, see what value it is, and then you will use that value to determine the number of bytes. So since this is a unique string, it's very easy to calculate the number of bytes you need to actually reach the instruction pointer. So let's restart the executable and run this second script. Hit play a few times, just make sure that we get this shown up, because that means it's actually binded to the port. And Python Brainpan1.py. Waiting. I'm not sure why this isn't working. Let's look at the script. Yep, that's all right. Let me just... I guess I'll just restart. Try one more time. There's a lot of trial and error with this kind of thing. Good, we're listening. And there we go. So I don't know. So after that little hump there, we have this new value in our EIP, which is 357.24134. And at this point, you would use MSF Venom to calculate the offset. In this case, I used an online pattern generator, and it told me that the offset was 524. The reason I use an online pattern generator again is because I don't have copying enabled and I can't figure out how. If any of you know, let me know in the comment section. And now that we've run that, we can, so we know we have 524 bytes of garbage that we need to send before we can write to the instruction pointer. So moving on to our third script, we have import socket, make a socket, and now we have a new buffer, which is 524 A's plus 4 bytes that will go in the EIP. And then we have an array of bad characters. And all this is it's every possible byte that'll be in our shellcode. And we want to see which ones are transformed, truncated, or just mess up the data around them. So some executables won't allow you to send certain bytes because they translate to something of different functionality. So for example, the null byte, which I've already removed. So in here would be /x00. That's a string terminator, which means that would be the end of our data. So the rest of the shellcode wouldn't work. For the Brainpan executable, I don't think there are any bad characters. I could be wrong. But I'm going to show you how to find them anyway. So if we restart this again, hit play a few times. Good, we're listening. Now, Python Brainpan1.py. You can see in our EIP, we kind of have the 1337. Not quite sure why it changed like that. But moving on, maybe it's because I use integer, not character or something. Disregard that. Anyway, what you want to see here is, if you notice the stack pointer is 005FF920. So we're looking at where the stack pointer points to right now. And you can see our character array here, starting with 01, 02, 03, 04, 5, 6, 7, 8. So if you see that there, what you would do to find bad characters is you would look and you would follow the sequence and say you got to 0A. And after 0A, instead of seeing 0B, you saw like 200 and something, and you saw a bunch of random characters after 0A. Or in the place where 0A should be. So if you got to 09, and then after 09 you just saw a bunch of random stuff, and it didn't follow the sequence, you would know that 0A was a bad character, because the server, when it received the byte 0A, it mishandled it, and it malformed the data around it. So therefore, all you do is you would remove 0A from your byte array. So you would just erase it, and then you'd send it again. You would repeat the process, and you'd look for the next bad character. So if you had 0A, then all the rest of this would be nonsense bytes, and you wouldn't be able to see the other bad characters. So you have to remove them one at a time, which is kind of a pain. So as long as you see that you have to examine the top of the stack and then follow the sequence of bytes, then you understand this part, and you'll do fine on the bad character section. You can see there. You can actually see we send $A's, then we send to what will go into the EIP, and then we sent our byte array. So moving on to the next script, this is the final exploit. So a quick word about this. The return address is where you want to jump to, what you want to put in the EIP, into the instruction pointer. In this case, we're going to use a gadget which jumps to the ESP. So as you know from our bad character array, we can write to the area that after the ESP, if that makes sense. And what we want to do is we want to jump to it. So we could put shellcode in place of this byte array here. And that's where we could store our shellcode. So obviously we want a way to fill, in place of this 13337, we want to fill it with the address of a gadget that will jump to this address here and then execute our shellcode. So the way to find that, I've put the command down here in the bottom. I don't actually have Mona installed on here, so I can't demonstrate it. But all you do is you would do mona-r jump ESP or something like that, something along those lines, and then it would give you an address of the instruction, and you would convert it to little endian. I'll leave that to you to figure out, and then you would put it here. And then this right here is a NOP sled, so NOP or no instruction. A lot of people say no op, I don't really get it. And all it'll do is, if you don't land exactly at the start of your shellcode, it will basically pass through the no operations until it reaches the actual machine code or the shellcode. Oh, whoops. So that's what this is for. And then we have our actual shellcode. And the way I generated this is with this command here, msvenom-p for payload, Windows/shell_reverse_TCP. So this is what's called a non-staged payload. And a non-staged payload means that the shellcode will just initiate the reverse shell without anything fancy. So an example of something that a staged payload would do is it would have shellcode to read other shellcode from a socket. So if space was a problem, you could do something like that. And another note with staged versus unstaged payloads, if you're going to use netcat as a listener, you need an unstaged payload. So moving on, we have lhost. I'm going to use the IP address of my Windows machine, because that's where we're testing. I'm going to listen on 4444. The only bad character we found was the null, format Python, and shellcode. So you can see it encoded our shellcode with Shikata 9. That's very nice. And this is all our shellcode. So, moving on to the script, we make a final variable, which will be our A's, which we need to reach the extended instruction pointer. Then what we want to put inside the extended instruction pointer, which is this address I put here, the address we want to return to. And then we have our sled, which is just our no operations, and then we have our shellcode. So the way this works is we'll make a socket, we'll send all the A's, then we'll be right at the boundary between the base pointer and the return address. We'll write this into the return address. The server will jump to this, and then we send our sled, our no operations, and our shellcode that will be executed. And then once again, we're just encoding this with the UTF-8. To get a shell from this thing, and I figured out what I was doing wrong. My setup is really kind of complex and wacky, between having to switch from host-only networks to bridged so I could, transfer my shellcode that I generated and stuff like that. So I decided to just take my proof of concept in the exploit that we developed here and just transfer it to Linux and just go straight at the box. You can see that we've received a shell from the actual machine. So, long story short, here's the exploit. This one worked. I had to generate new shellcode for Linux, because I actually decided to test the proof of concept against this box right here. And then, as you can see, we have that address. And everything's pretty much the same, so we pretty much did everything, just ran into some technical difficulties, but now we have a shell. You can see we can actually run commands and stuff like that. I used a staged payload, as you can see here. I'm not going to run through the privilege escalation. The point of this box was to learn the buffer overflow, and hopefully you've done that. So, yeah, this was really fun. Again, this is pretty, as far as binary exploitation goes, this is pretty basic. I hope to improve my binary exploitation. Just be aware that this is like what they call vanilla, very standard. But I hope you learned a lot, and I hope you understand the value in knowing the theory behind how the stack works and how we actually are able to write to the return address. So until then, I'll see you guys next time.